Hello everybody, and welcome to exercise 5 on page 32 of the workbook. And this is not going to be a complete solution to this problem. We're just going to pick a couple of the parts and go through them. You can look at the solutions to the other parts in the written solutions here. Okay, so this is an example of actually algebraically calculating partial derivatives of functions. Okay, you may have done a little bit of work with this in your Calculus 2 class. Maybe not, that's okay. The good news about algebraic calculation of partial derivatives is if you can calculate an ordinary derivative from Calc 1, you can calculate a partial derivative. There's just one thing that you need to keep in mind when you do that. Okay, so I'd like to start with part B of this. Okay, and just do that because I think that's maybe the easiest function. Okay, they want us to take the partial derivative with respect to each independent variable, okay, and this function, and when they say independent variable, they mean input variable. Okay, so this has two input variables, x and y. So let's first take the derivative with respect to x. Partial z, partial x. Okay, so notationally, we're going to take the derivative with respect to x of x squared y plus y squared x. Okay, and let's break that into two parts here. Okay, so there are two terms that we need to take the derivative of, one by one. Okay, and if we start with the first one here, the thing to remember when you're taking this derivative is if x is our variable, we're treating y as a constant. Okay, that seems odd, but that's the way partial derivatives work. So that y that you see there, you're going to treat that the same way that you would a number, which means that we can actually take that y and factor it outside of the derivative. Just the same way that we could if that y were a 2, some number. Okay, and then moving over to the derivative on the right here, same thing is true. Y is being treated as a constant, and so that y squared is like one big constant that we can pull outside of the derivative. Okay, and so in taking the derivative, we've got a y that's just kind of coming along for the ride, and then the question is, what is the derivative of x squared? That's just 2x. Okay, and then over here to the right, the derivative with respect to x of x is just 1, and so we wind up with an answer, if we simplify, that looks like 2xy plus y squared. Okay, there's our derivative with respect to x. Okay, let's take a look at the derivative with respect to y then. Okay, and again, this is going to break into two pieces. Okay, and same idea here, but this time it's y that's our variable. We're taking the derivative with respect to y, which means that any x's that you run across are going to be treated like constants, and so we can pull those out of our derivative, so we're going to get x squared times the derivative of y with respect to y plus x times the derivative of y with respect to y squared. Okay, so the x squared is coming along for the ride, and the derivative of y is just 1. Okay, and then over here, the derivative of y squared is just going to be 2y. Okay, simplify that, and we're going to get an answer of x squared plus 2xy. Okay, so there's our derivative with respect to x, and there's our derivative with respect to y. Okay, the two answers that we've got here. All right, so you can kind of see that the key is keeping track of what your variable is and what you're treating as a constant when you take these derivatives. All right, let's back up and do part A now to this. Okay, now this is interesting because f has three independent variables, three input variables of x, y, and z. So we actually need to take three separate partial derivatives here. And let's start with the derivative with respect to x. I could either write that partial z partial x, or I could write it like this, fx. Okay, and that just means that we're going to take the derivative with respect to x of this function. Okay, so if we're taking the derivative with respect to x, that means that we're treating y and z as if they're constants. Okay, so in particular, this z that you see here, that's being treated as a constant, which means we're free to pull that outside of our derivative. And all that's really left to take the derivative of is ln of y cosine of x. Okay, how would we do that? Well, we need to think back a little bit to calculus 1. How do we take the derivative of a natural log? Well, we're going to get 1 over, and notice that there's a chain rule involved here. It's the natural log of y cosine of x. So we're going to get a derivative of 1 over that entire inside part. And then the chain rule says we need to multiply by the derivative of the inside. Okay, y cosine of x. All right, I'm just going to make a note that we use the chain rule at that step. Okay, so taking a look at what we have, we are done with the first two pieces here, so I'm just going to rewrite those. So z times 1 over y cosine of x. And what's left to do is to take this derivative here. Okay, and notice again, we're taking the derivative with respect to x, so this y is being treated as a constant. We can pull it outside. And all we really need to take the derivative of is the cosine of x. That derivative is going to be negative sine of x. Okay, and so we've taken the entire derivative. It looks like this. That would be a perfectly okay final answer. If we want to simplify a little bit, we could consolidate some things together and maybe put the z, the y, and the negative sine x all in the numerator. Okay, and oh, actually, wait a minute. We can do a little bit better than that. Okay, so notice that there's a y that can cancel. Let's do that first, and then we'll consolidate this into one fraction. Okay, so in the top, we're going to get a negative z sine of x. Okay, and in the bottom, we're just going to get the cosine of x. Either of those two answers would be okay. One's just a little bit more simplified. Okay, so we've taken the derivative with respect to x. We are ready now to move on to the next independent variable. What would the derivative with respect to y look like? Okay, well now we're taking the derivative with respect to y of our whole function. Okay, again, y is our variable, so z is being treated as a constant, so we might as well go ahead and pull that outside. Okay, we come to a similar situation that we had a minute ago. We need to take the derivative of ln of y cosine x, so we're going to use the chain rule. And derivative of ln of something is 1 over that something. Times the derivative of the inside, this time with respect to y. Okay, so we are done with the first two terms. The z times 1 over y cosine of x, let's just rewrite those. Okay, and then, since we're taking the derivative with respect to y this time, it's the cosine of x that's being treated as a constant. Okay, so that can be pulled out. And all that's left to really take the derivative of is this y. And if you take the derivative of y with respect to y, you're just going to get 1. Okay? So there would be our derivative with respect to y, and if we want to, we could simplify that, maybe put it into one fraction and cancel. So the cosine of x's are going to go away, and it looks like we're just going to get z over y out of this. Kind of a nice simple derivative this time. Okay, and then finally, what about the derivative with respect to z? Okay, well, for this piece, z is our variable, which means that y and x are being treated as constants, and so this entire piece that I'm circling, ln of y cosine of x, that's like one big constant because it just has y's and x's in it, which means we can pull that entire thing out of our derivative. Ln of y cosine of x, all that we really have to take the derivative of, whoops, not x, z, is z. Okay, but what's the derivative of z with respect to z? It's just 1, and so we're just going to get ln of y cosine of x. Okay, and so actually our derivative with respect to z is the one that turns out to be the simplest out of the three.